Good morning. Today we are going to discuss about numerical solution of ordinary differential equations. Myself, Ali Varghese, College of Engineering, Pathanavaram, and from Department of Mathematics. So here we are going to discuss an first degree ordinary differential equation, which is of the form dy by dx is equal to f of xy. That is, usually uh, we are dealing with initial value problems, that is a differential equation together with an initial condition y at x naught is equal to y naught. The value of y at the point x naught is given. So a differential equation is given and an initial condition is also given, and we have to solve this differential or this initial value problem. So this kind of problems are known as initial value problems, and we are looking for a solution. So we know how to calculate an analytical solution for such a problem. First, solve the differential equation dy by dx is equal to f of xy using some analytical methods which we had discussed in the class of ordinary differential equations in previous semesters, and that solution may contain a number of arbitrary constants, and that arbitrary constant can be eliminated using the initial conditions y at x naught is equal to y naught. So that is how we calculate an analytical solution for a differential equation. So, but in some cases, finding an analytical solution need not be simple. Some cases it's not possible, and in some cases such a calculation is not simple, it is a tedious process. So uh, we are discussing about some numerical methods by which we can find out a solution to the given differential equation or given initial value problem. So by the time numerical solution, we are uh, looking for a function y is equal to f of x whose values are tabulated, or in other words, we are looking for the value of y at say some points x1, x2, etc., xn, or the value of y at x naught, that is y naught is given, that is uh, x naught and y naught is given as the initial conditions, and we are looking for the values of y at points x1, that is y1, at x2, that is y2, etc. And in our methods, we choose the values of x1, x2, x3, etc. are equidistant points. They are equally spaced, evenly spaced through the x-axis, and the difference between two successive points is represented by h. So x1 is x naught plus h, x2 is x1 plus h, x3 is x2 plus h, and so on. In exam point of view, the value of h may be given in your questions itself, or we can choose a reasonable value of h. Uh, in this session, we are going to discuss about three methods: Euler's method, improved Euler's method, and Runge-Kutta method, which are three important methods to use, which is used to solve initial value problems. And uh, we are following the textbook by Erwin Kreyszig named Advanced Engineering Mathematics. Uh, and we try to follow the methods and representations and terminologies used in this particular textbook. Then we start with the simplest one, Euler's method. It is based on the formula yn plus 1 is equal to yn plus f of xn yn. So that is a recurrence formula. The value of yn plus 1 is given in terms of yn and the value of the function at xn by n. So remember, f of xn by n is given by our equation number 1, that is dy by dx is equal to f of xy, and this is not the solution, it is the value of dy by dx. Now the initial values are given by the initial value conditions, that is y at x naught is equal to y naught. So the values of x naught and y naught are given in the problem itself, and f of xy is also given in the problem. So we start with x naught, y naught and calculate the value of y1. Then using x1 and y1, we calculate the value of y2 and so on. And we illustrate the concept of Euler's method using a simple problem, and we use the same problem to illustrate the other two methods. So we consider a simple differential equation dy by dx is equal to x plus y, and an initial condition is given y at 0 is equal to 1, that is the value of y at x is equal to 0 is equal to 1, and we have to solve the equation at the points x is equal to 0.2, 0.4, etc. 1.0. So in other words, we are looking for a tabulated function in the interval 0, 1. And here the difference between two successive points are h is equal to 0.2 and f of xy is equal to x plus y. Now here f of xy is equal to x plus y and h is equal to 0.2. So the value of y1 using the formula, that is n is equal to 0, we get y1 is equal to y naught plus h into f of x naught y naught, that is 1 plus, that is value of y naught is 1, x naught is 0, and substituting in the equation it is 1 plus 0.2 into f of 0, 1. F of xy is equal to x plus y, so f of 0, 1 is equal to 0 plus 1, so it is 1 plus 0.2 into 0 plus 1 is equal to 1.2. Now y2 is calculated using the value of y1, that is 1.2, and x1 is x naught plus h, that is 0.2. So y2 is equal to y1 plus h into f of x1 y1, that is 1.2 plus 0.2 into f of x1, that is 0.2, y1, that is 1.2. Substituting in the expression, we get y2 is equal to 1.48. y3, using the values of y2 and x2, y2 is 1.48 and x2 is 0.4. So y3 is calculated as 1.856, and y4 is equal to y3 plus h into f of x3 by 3. x3 is obtained or x3 is x2 plus h, which is 0.6, and y3 is obtained in the previous step as 1.856, and substituting we get y4 is equal to 2.3472. And similar in the next step, y5 is the value of y at x5. So x0 is equal to 0, x1 is equal to 0.2, x2 is equal to 0.4, x3 is equal to 0.6, x4 is equal to 0.8, and x5 is equal to 1, and y5 means the value of y at 1, that is given by y4 plus h into f of x4 y4, which is 2.3472 plus 0.2 into f of x4, that is 0.8, y4 obtained in the previous step, 2.3472, is equal to 2.97664. Can be round to 4 decimal places as 2.79766. And if you tabulate this function as x naught, y naught, x1 by 1, x2 by 2, x3 by 3, etc., x5 by 5, then that will give a tabulated function which is the solution of our differential equation dy by dx is equal to x plus y subject to the initial condition y of 0 is equal to 1. And here we tabulated the solution and we compare it with the exact solution, that is we solve the differential equation using analytical methods which give the solution as y is equal to c into e raised x minus x minus 1. So the method we can use here is okay, it is a linear equation and therefore we can solve it as the solution can be obtained as complementary function plus particular integral, and that gives the value of y as c raised x minus x minus 1. And we can eliminate the arbitrary constant c using the initial condition y of 0 is equal to 1, and that will give the exact solution y is equal to 2 e raised x minus x minus 1. Then we calculate the value of y using the exact expression 2 e raised x minus x minus 1. That's the actual value of y corresponding to the value of x. And we tabulate it together with the value obtained by Euler's method. And we tabulate it in the following table. And the value of y obtained in Euler's method and the exact solution are not exactly the same. There is a difference between them, and that's the error in Euler's method. And if you look at the values at point 2, there is an error of 0.0428, and at point 4 the error become larger, and as the value of x move away from the initial conditions or initial value of x naught, the error become larger. And Euler's method is not an efficient method or not a method which contains which generate less error. It give a lot of error, but the method is very simple and very straightforward. It merely depends on the concept of tangents. And okay, we know that dy by dx gives the slope of the tangent at a particular point, and we use that implication of that concept to find or to approximate the solution curve by a sequence of tangent curves. Anyhow, here it's very obvious that Euler's method is not an efficient method, or it's not a perfect method to calculate derivatives. So we improve the Euler's method, and that method is known as an improved Euler's method, and it uses a formula yn plus 1 is equal to yn plus h by 2 into f of xn yn plus f of xn plus 1 yn plus 1 star. It's an iterative method. Here obviously yn plus 1, the value of y in the n plus 1 or value of y at n plus 1 point is represented in terms of yn, f of xn, yn, and f of xn plus 1 and yn plus 1. That is the slope at the point xn yn and the slope at the point xn plus 1 and yn plus 1. And the slope at the point xn plus 1 and yn plus 1 is not readily available, we use uh, Euler's method to calculate an approximate value of xn plus 1 and yn plus 1, and we use that value in the form equation number 3 as an iteration formula, or we use the equation number 3 as an iteration formula to refine the value of yn plus 1 until we get a required amount of accuracy. So here the value of yn plus 1 is the value of yn plus 1 obtained in the previous step is represented by value yn plus 1 star, and we start with the value of yn plus 1 which is obtained by Euler's method. So if you consider the previous problem, to calculate y1 we use the formula as y1 is equal to y0 plus h into f of x0 y0, which is our Euler's formula. That will give the value of y1 as 1.2. So that's the initial value obtained for y1, and we refine the value of y1 using the formula given in equation number 3. So y1 is recalculated as y1 is equal to y0 plus h by 2 into f of x0 y0 plus f of x1 y1 star. Y1 star is the value of y1 obtained in our previous iteration, here obtained in our Euler's method, that is 1.2. Substituting y1 is equal to y0, that is 1, plus h by 2, 0.2 by 2, 1.1 into f of x0 y0. x0 is equal to 0, y0 is equal to 1, so 0 plus 1, plus f of x1 y1 star. x1 is 0.2, y1 star, value of y1 obtained in our previous step, that is 1.2, that is 0.2 plus 1.2 is equal to 1.24. So that is a new value of y1. And again, in our next step, y1 is equal to y0 plus 0.2 by 2 into f of x0 y0 plus f of x1 y1 star. So if you compare this formula with the formula in the previous iteration step, the only change is in y1 star. So we just replace this 1.2 with 1.24, and it becomes 1.244. So in our next step, this y1 star is replaced with 1.244, and that will give 1.2444. So here the answer contains 4 decimal places, and in the next step, when we replace y1 star with 1.2444, we get 1.2444, which is approximated as 1.2444 to 4 decimal places. So we repeat the same set of values, and we can stop here, and the value of y1 is 1.2444, correct to 4 decimal places. Now this is the method to calculate the value of y2. We start with calculating the value of y2 using Euler's method as y1 plus h into f of x1 y1, which is equal to y1 is 1.244 plus 0.2 into 0.2 plus 1.2444. So using the value of y1 obtained in our first iteration method, we calculate the value of y2, and it is approximately is equal to 1.5333. Now we refine this value of y2 using the iteration method, and y2 is equal to y1 plus h by 2 into f of x1 y1 plus f of x2 y2 star. So y2 star is the value of y2 in our previous iteration, here it is 1.5333. Then it is y1, that is 1.2444 plus h by 2, that is 0.1 into f of x1 y1. x1 is 0.2, y1 is 1.2444 plus x2 is 0.4, y2 star, that is value of y2 obtained in our last step, is 1.5333, and calculating the value is 1.5822. So in our next step we replace y2 star with 1.5822, and that will give here the only changes in y2 star. Y2 star is replaced with 1.5822, and that will give 1.58706, which is approximated as 1.5871. Next step, we replace y2 star with 1.5871, and that will give the value of y2 as 1.5876. And next step, we replace y2 star with 1.5876, and that will give y2 is equal to 1.5876. So same value in these two consecutive steps, and that means the value of y2 can be approximated as 1.5876. So we just solve it for two values. X is equal to 0, it's given, x is equal to 0.2, and x is equal to 0.4, and that values are tabulated here together with the values obtained in Euler's method and exact solution. So the value of y is given, so they are the same for all the three cases, and value of y at point 2. The exact value is 1.2428, and the value obtained by improved Euler's method is 1.2444, and there's a small difference, or there is an error, but it is much lesser than the error obtained or the error in Euler's method. And when we go to the next point, the value of y at 0.4, the error become so here the difference between the value in improved Euler's method and exact Euler's exact solution is of order of 0.004640, etc. But the difference between exact solution and Euler's method is 0.1, so that's much larger than improved Euler's method. So comparatively, improved Euler's method gives much lesser error than Euler's method, but it takes a little more calculation or a little more work to find the solution. So in exam point of view, if you are requested to calculate the value of y at a number of points, 4 or 5 or 6 points, then I strongly recommend to use Euler's method. And if you are required to find out the value of y at only 2 points, like in this problem at point 2 and point 4, or point 1 and point 2, only at 2 points, then I strongly recommend to use improved Euler's method instead of Euler's method. And in practical situations, we can easily write a simple program to execute either Euler's method or improved Euler's method. So the iteration process is not a tedious task when we depend on some programs or some calculators. So it's not a big issue. We are usually concentrating on improved Euler's method. And now we have the Rangekutha method, which is more practical and more accurate method than the Euler's method and improved Euler's method. And we are here concentrating on fourth order Rangekutha method, which is the most efficient in our lot. And there are second order and third order for Rangekutha methods, but this is the most efficient one, and so we concentrate on the Rangekutha methods. And this will give uh, or the method is like this. The value of yn plus 1 is yn plus 1 by 6 into k1 plus 2 into k2 plus 2 into k3 plus k4, where these values of k1, k2, k3 and k4 are given by k1 is equal to h into f of x and yn, and k2 is equal to h into f of xn plus h by 2 yn plus k1 by 2. K3 is equal to h into f of xn plus h by 2 yn plus k2 divided by 2, and K4 is equal to h into f of xn plus h yn plus k3. And we will illustrate it using um, a problem, the same problem, I think. And number one thing, this is not an iteration method. This will give the value of yn plus 1 in a single step. So here f of xy is x plus y is 0 is equal to 1, or y at x naught is equal to 1, and h is equal to 0.2. That's our extra problem. So we start with calculating the values of k1, k2, k3 and k4. k1 is equal to h into f of x naught y naught. H is equal to 0.2. X naught is 0, y naught is 1, and substituting we get k1 is equal to 0.2. Then k2 is h into f of x naught plus h by 2. X naught is 0, h is 0.2, 0.2 by 2, that is 0.1, and y naught plus k1 by 2. K1 is obtained as 0.2, 0.2 by 2. Y naught is 1. So it is f of 0.1, 1.1. So 0.1 plus 1.1 into h, 0.2. That is for 0.24. And k3, that is h into f of x naught plus h by 2. As in the previous case, the value is 0.1. And y naught plus k2 divided by 2. K2 is 0.24. Divided by 2 is 0.12. So 1 plus 0.12, that is 1.12, and the x ordinate is x naught plus h by 2, that is 0.1. So 0.1 plus 1.12 into 0.2, that is 0.244, and k4. So there's a small difference in the expression for k4 compared to k3 and k2. K4 is h into f of x naught plus h. X naught plus h is actually x1, and that is 0.2. And y naught plus k3. Y naught is 1. 1 plus k3 is 0.244. So it is 1.244. And x plus y is 1.244 plus 0.2, that is 1.444 into 0.2 gives 0.2888. Then we substitute in our equation number 1, that is y1 is equal to y naught plus 1 by 6 into k1 plus 2 into k2 plus 2 into k3 plus k4. Substituting the values, it is y naught, that is 1 plus 1 by 6 into k1 0.2 plus 2 into k2 is 0.24 plus 2 into k3 is 0.244 plus k4, that is 0.2888, and that will give 1.2428, correct, to 4 decimal places. So whenever we got here, okay, whenever we get value of k1, k2, k3, k4 which contains more than 4 decimal places, we can round it to 4 decimal places. And to calculate the value of y2 using the value of y1, it's again y2 is given by y1 plus 1 by 6 into k1 plus 2k2 plus 2k3 plus k4, and we start with calculating values of k1, k2, k3 and k4. k1 is equal to h into f of x1 y1, which is 0.2 into f of x1, that is 0.2. y1 in the previous step it is obtained as 1.2428, as equal to 0.2 into f of xy is x plus y, so 0.2 plus 1.2428 is equal to 0.28856. So it is rounded as 0.2886. Then k2 is h into f of x1 plus h by 2, that is 0.2 plus 0.2 by 2, that is 0.3, and y1 plus k1 by 2, y1 is 1.2428 plus k1 is 0.2886 and 0.2886 divided by 2. So what we obtain is zero point 0.2 into the x value is 0.3, y value is 1.3871. So the value of k2 is obtained as 0.33742. It is rounded as 0.3374. Then k3 h into f of x1 plus h by 2, that is 0.3, and y1 plus k2 by 2, y1 is 1.2428 and k2 is 0.3374, and what we obtain is 0.3423. Then k4 value, it is h into f of x1 plus h, x1 plus h. x1 is zero point 0.2, h is 0.2, so it is 0.2 plus 0.2, that is 0.4. Is a mistake. It is 0.2 plus 0.2, not 0.1, it's 0.2. And here it is y1, that is 1.2428 plus this is k3 0.3423 and is equal to 0.37702, which can be rounded as 0.377. So substituting in the expression for y2 is equal to y1 plus 1 by 6 into k1 plus 2 into k2 is 0.3374 plus 2 into k3 0.3423 plus k4 0.377 is equal to 1.5803. So that's the value of y2, that is the value of y at x2. x2 is equal to 0.4. So value of y at 0.4 is 1.5803. Now again we just tabulate the value obtained by RK method or Ragakuta method in a table for this comparison purpose uh, together with the exact solution. So observe the value obtained in RK method is exactly the same as the value obtained in our exact method up to 4 decimal places. It is much better than improved Euler's method and Euler's method. When you consider the value of y at the point 0.4, it's better than both improved Euler's method and Euler's method, but it contains a little error. So as we move away from the starting point, the solution may contain some error. So this is the comparison between three methods, and to improve the solution or quality of the solution, the best thing is to take the value of h as small as possible. So here the value of h is taken as 0.2, and we use that to calculate the value of y at 0.2 and 0.4. And if you take the value of h as say 0.1, and if we use that value to calculate the value of y at 0, 0 0.1, 0 0.2, 0 0.3 and then 0 0.4, instead of 2 steps we had to include a lot of calculations, and we obtained at the point 0.04 in 4 steps. If we move like that, then the solution will contain much less error than this one. So That's one method to reduce the error. Just reduce the value of h, and anyhow, as we move away from the value of x naught, this method will contain, or the value of y may contain more error as we move away from the value of x naught. So that is these are the three methods, and here we just illustrate the methods, and you have to go through a number of problems, numerical problems actually, numerical problems, and out of these three methods, RK method is very much important. Euler's method is a simple method, uh, and improved Euler's method is again important. Um, so just go through a number of problems based on uh, these three methods.